Something happened recently that most people never heard about. Across an entire region of our planet, radio signals went quiet. Not one signal, not one station. Signals across a broad stretch of ocean and coastline became unreliable and weakened for a period of time. No storm, no technical failure, no human explanation. The cause was something that happened on the sun. Stay with me, because in the next several minutes, we're going to walk through exactly what is happening on the sun right now, what already occurred and why it matters, what the second sunspot, which carries a more complex magnetic structure, is quietly doing, and what the next few days could bring for people right here on Earth. This is the kind of story that most major news outlets do not cover until after something notable has already occurred. A burst of energy, what scientists call a solar flare, erupted from a brand new sunspot that had just crept around the edge of the sun. That energy travelled across space and reached Earth in a matter of minutes, and when it arrived, radio communications across a large section of the Indian Ocean and nearby regions were temporarily disrupted. Ships at sea, aircraft over open water, weather monitoring stations, all of them touched by something that originated on a star. Now here is where this story gets genuinely interesting. The sunspot that caused that disruption is called AR4374, and right now it is rotating, slowly, steadily, into the position where it will be aimed directly at Earth, not at an angle. Not from the side, directly facing us. But AR4374 is not the only story here. Right alongside it, a second sunspot has appeared. Scientists are calling it AR4377, and unlike its neighbour, AR4377 has not fired yet. It has been building quietly, and according to the people who study the sun professionally, it carries one of the most dangerous types of magnetic structure a sunspot can have. The kind of structure that, when it releases, can produce more powerful flares than simpler sunspot regions. One sunspot has already produced a moderate flare that caused a temporary radio disruption. The second one has not fired at all. And both of them are moving into the position where they will be more directly facing Earth over the next few days before we go any further. If you find stories like this important, hit the like button right now. It takes 1 second, and it genuinely helps more people find information like this when it matters most. And if this is your first time here, hit subscribe. We cover the things happening in our sky and on our sun that most people never hear about until after the fact. Drop a comment below and tell me, where in the world are you watching from right now? Because if you are in a part of the world that experienced those radio disruptions, this story is personal for you, and I want to know. Now let us start at the beginning. Let us start with what actually happened, the flare, the blackout, and the sunspot that caused it. Because understanding AR4374's history is the key to understanding why AR4377 sitting quietly right next to it may actually be the bigger story. There is something worth understanding before we go further, and it is the kind of thing that reframes everything else. AR4374 did not simply appear out of nowhere and fire once. This sunspot had a history before it ever became a headline. It had been active before anyone was paying close attention, and the fact that it fired the moment it came around the sun's edge, before forecasters had even fully confirmed its position, says something important about its character. It is not a passive region of the sun waiting to be noticed. It is an active one, and that distinction matters enormously when you consider that its neighbour, AR4377, has been almost completely silent. Sometimes the most significant thing a sunspot can do is nothing, not because it lacks energy, but because it is storing it. Solar scientists pay extra attention to quiet regions that carry a complex magnetic structure. They find it notable, meaningful, worth watching very carefully. And that is exactly what is happening right now. Around the clock, across multiple continents, teams of professional forecasters are watching both of these regions as they complete their rotation toward the most critical position in relation to Earth. This story has layers, and each layer matters, so let us go through them one at a time, starting with what happened during that flare, why it affected real people in the real world, and why AR4374 coming back into view was not a surprise to the scientists who had been tracking it since early February. Let me take you back to the early hours of a recent morning. The sun had been relatively quiet for several days before this. Forecasters at NOAA, the United States agency that monitors space weather around the clock every single day, had been watching a mostly calm solar disk. No major eruptions, no significant alerts, just the ordinary low-level activity that always hums beneath the surface of our sun. And then, without much warning, something changed. A burst of energy erupted from the sun's eastern edge, the side from which new regions rotate into our view as the sun turns. Think of a solar flare like this. Imagine a camera flash, except instead of lighting up a small room, this flash travels across the distance between the sun and Earth in roughly 8 minutes. And when it arrives at Earth, its effects are immediate and can be felt across large regions within minutes. It interacts with the upper layers of our atmosphere in a way that interferes with radio signals, high-frequency radio, the kind used by ships navigating open ocean, aircraft flying over water without GPS backup, and weather monitoring stations spread across remote regions, absorbs that energy and loses coherence. Signals that were clear a moment ago simply go dark. That is what happened. NOAA classified the event as an R1 radio blackout, the lowest level on their official 5-point scale. And it is worth pausing on that for a moment, because the word lowest might suggest it was barely noticeable. It was not. Even an R1 event touches real operations in the real world. Pilots flying transoceanic routes depend on radio. Ships navigating stretches of ocean that still rely on traditional radio communication felt that disruption. The scale does not measure inconvenience, it measures impact. And even at the lowest level, the impact is real. Now here is the part of this story that most people missed entirely. AR4374, the sunspot responsible for that flare, was not new to the scene when it fired. This region had first appeared and rotated into view around the beginning of February. When it first came over the sun's eastern edge at that time, it was already active. Within days of becoming visible, it had already produced a notable flare. AR4374 is a brand new sunspot region. It has been active since the very first days it appeared over the sun's eastern edge in early February. And as it continued rotating into view, it made its presence known immediately. This is how the sun works. New active regions appear over the edge as the sun rotates, and as they move across the face toward Earth, their activity can build or change. And as it moved further into view, it did not wait to announce itself, it fired the flare. Before forecasters had fully updated their reports on its position, the energy was already heading toward Earth. That tells you something important about this region. It is not waiting for a perfect moment. It is not building slowly and deliberately toward one significant eruption. AR4374 has shown a consistent pattern of producing moderate-level flares. It erupts at moderate levels with a consistency that has had solar scientists watching it closely since it first appeared. The fact that it produced a flare strong enough to cause an R1 blackout, and did so while still rotating into position, means that as it moves toward the center of the Earth-facing disk, the geometry improves. Flares from the edge of the sun often send energy at a glancing angle in relation to Earth. Flares from the center of the disk send energy more directly toward us. As AR4374 moves closer to that central position, any eruption it produces becomes more likely to be aimed straight at Earth rather than off to the side. The region is active, the geometry is improving, and the forecasters who track it are watching its magnetic complexity measurements every single day. But here is the thing, and this is where the story gets more interesting than most people realize. While all of this was happening with AR4374, while the radio blackout was making its way into space weather reports, while forecasters were updating their assessments and tracking the rotation, right next to AR4374, another sunspot was quietly developing, getting larger, getting more complex, and not producing anything dramatic at all. That silence was not nothing. That silence had a name, and that name was AR4377. There is an old observation that the loudest thing in the room is not always the most significant one. AR4374 made noise. It caused a radio blackout. It has been active since it first appeared in early February and has already produced notable flares. It is the kind of sunspot that announces itself clearly and gets written about in space weather reports. And that is fine. It deserves that attention. But while everyone was watching AR4374, tall AR4377 was doing something different. It was building. The Royal Observatory of Belgium, one of the most respected and long-standing solar monitoring institutions in the world, analysed AR4377's magnetic structure and published their findings in their regular solar bulletins. What they described is something that solar scientists treat with particular seriousness. AR4377 has what is classified as a beta-delta magnetic configuration. Let me explain what that means in plain terms, because the label matters less than the reality it describes. Every sunspot has a magnetic structure. Think of that structure like the internal wiring of a battery or a spring mechanism. Most sunspots have relatively straightforward magnetic arrangements. Energy can build up within them, but it releases gradually. And the flares they produce tend to be small and manageable. They are common. They are not particularly alarming. They are simply the sun doing ordinary sun things. A beta-delta configuration is something else entirely. Imagine that instead of a spring that releases its energy gradually as it uncoils, you have a spring that has been compressed tightly, coiled against itself in a way that prevents gradual release. The energy does not bleed out slowly. It stays stored. And when the structure finally becomes unstable enough to break, it releases that stored energy all at once in a single eruption. The flares that come from beta-delta regions are not necessarily more frequent than flares from simpler sunspots, but they can be significantly more powerful. AR4377 has that compressed structure right now. And so far, through days of observation and careful measurement, it has produced almost nothing. B-class flares, which are the smallest category on the solar flare scale, practically invisible in any practical sense. So small that most monitoring reports barely mention them. The spring is still compressed. This is precisely what makes forecasters pay attention to AR4377 in a different way than they pay attention to AR4374. AR4374 shows you what it can do regularly. Its history is visible. Its behavior is relatively predictable in the sense that it tends to erupt at moderate levels and has done so consistently. You know what you're dealing with. AR4377 has shown you almost nothing. In solar science, a quiet region with a complex magnetic structure is treated as one to watch carefully. A region that has the structure to produce powerful eruptions but has so far remained quiet, which forecasters continue to monitor carefully. Solar scientists note that regions with this type of magnetic structure sometimes produce their strongest eruptions after a quiet period, though this is not guaranteed the magnetic structure was there. The energy was stored. When a release did occur, it was sometimes stronger than the quiet days before it had suggested was coming. No one is saying AR4377 will do that. Forecasters are careful, and they are specific about the difference between what is possible and what is probable. What they are saying, clearly, in their daily bulletins, is that AR4377 has the structure that puts it in a different category than most active regions currently on the Sun. It warrants elevated attention, it warrants daily monitoring, and it warrants the kind of careful watch that experienced solar scientists give to regions that have not yet revealed their full potential. Meanwhile, day by day, both AR4374 and AR4377 are rotating across the Earth-facing side of the Sun. They are not sitting still. The Sun never does. And their rotation is what makes the timing of this story so precise, so specific to the next few days, as opposed to last week or next month. Understanding what that rotation means, and why the center of the Earth-facing disk is the position every forecaster is watching both sunspots approach, is the next piece of this story. Because the geometry of the Sun's face in relation to Earth is not uniform. Where a sunspot sits when it fires matters enormously, and right now, both AR4374 and AR4377 are heading toward the position that matters most. Before we go further into where this is heading, let me take a moment to step back. Not because this story needs to slow down, but because I want to make sure everyone watching fully understands what we are actually talking about. Not in a way that feels like a science lesson, in a way that makes the rest of this story land correctly. What is a sunspot? If you have ever looked at a photograph of the Sun taken through a proper telescope, you may have noticed dark patches scattered across its surface. Those are sunspots, and the first thing most people assume when they see them is that they are holes, gaps, or missing pieces of the Sun's surface. They are not. Sunspots are regions where the Sun's magnetic field has become so concentrated, so intensely tangled, that it actually prevents some of the Sun's internal heat from reaching the surface in that spot. Because they are slightly cooler than the surrounding surface, they appear darker in photographs. On a star that burns at temperatures most human minds cannot meaningfully picture, slightly cooler still means extraordinarily hot. But the contrast is enough to make them visible. Those dark patches are not holes. They are areas where strong magnetic forces hold back some of the Sun's heat from reaching the surface and that magnetism is exactly why sunspots matter. Because when that magnetic field becomes sufficiently unstable, when it reaches the point where it can no longer hold its stored energy, it releases suddenly, in the form of a solar flare, a burst of radiation and charged particles that travels outward from the sun in all directions. Most of the time, the energy goes off in directions that have nothing to do with Earth. It flows into the vastness of space and affects nothing we would ever notice. But when a flare occurs on a sunspot that is facing Earth, that energy heads directly toward us, and it arrives quickly, faster than most people would expect. The radiation component arrives in roughly 8 minutes. The particles themselves take longer, depending on their energy level. And a coronal mass ejection, a large cloud of solar material that sometimes follows a flare, can take a day or more to arrive, depending on how fast it is moving and what path it takes through space. When that energy reaches Earth, it does not disappear. It interacts with our planet's magnetic field and our atmosphere. And our modern world, built on invisible signals and connected technology, feels those interactions in ways that our grandparents simply would not have noticed. Think about what you actually use every day that depends on signals travelling through or near the atmosphere. The GPS in your car and your phone, radio-assisted navigation, satellite communications, the systems that run precision agriculture, coordinate emergency services, and guide aircraft across oceans. All of these technologies live in a world that the sun can reach out and touch. Your grandparents did not have GPS. They did not rely on a network of satellites orbiting at precise positions in space. They did not operate the kind of interconnected communication infrastructure that now spans the globe. A significant solar flare in their era might have disrupted some telegraph communications, and in the most extreme historical cases it did. But the scope of what could be affected today is fundamentally different, not because the sun has changed, but because we have. This is not meant to alarm you. It is meant to give you an accurate picture of why space weather monitoring exists, why NOAA maintains a team of forecasters dedicated specifically to this, and why institutions like the Royal Observatory of Belgium issue daily solar bulletins that are read by satellite operators, power grid managers, and aviation authorities around the world. The sun affects the world you live in, not in dramatic, visible ways most of the time, but in the quiet, technical ways that modern life depends on. And when two sunspots with active and complex magnetic structures are rotating into the position where they face Earth most directly, that is when the monitoring networks pay the closest attention. Because the geometry matters, the position matters, and right now, the position of both AR4374 and AR4377 is moving in a specific direction that forecasters are tracking with precision. Understanding that rotation, what it means, how it works, and why the next few days represent the critical window, here is something that most people who watch the sun casually never fully account for. The sun does not sit still. Like Earth, the sun rotates. Its entire surface, or more precisely its outer layers, since the sun is a ball of plasma and different latitudes rotate at different speeds, is constantly turning. And because it turns, any sunspot that appears on one edge of the sun will gradually travel across the entire visible face, a journey that takes roughly 13 to 14 days, and eventually rotate out of view on the other side. This rotation is not dramatic or fast. It is steady and unhurried. You cannot watch it happen in real time with the naked eye. But the solar monitoring cameras that NOAA and other institutions use, updated continuously, capture that movement in time-lapse form, and it is clearly visible over the course of days. AR4374 came over the sun's eastern edge, the left side of the disk as we see it from Earth, and began rotating toward the center. The center of the Earth-facing disk is the position that matters most for Earth impact. When a flare occurs from a sunspot at the center of the disk, the energy it releases is aimed as directly at Earth as it can possibly be. When a sunspot is at the center of the sun's disk, any energy it releases is aimed more directly at Earth than from any other position. Any flare or cloud of solar material from that position would travel more directly toward Earth than from the sun's edges. Sunspots that erupt from near the edges of the disk often send their energy at an angle that means Earth receives only a glancing effect, or misses altogether. The same flare that would cause significant effects from the center of the disk might barely be noticeable if it fired from the sun's edge. Right now, AR4374 is moving through that critical zone. AR4377 is moving alongside it. Think of it as two travelers walking the same road in the same direction, at roughly the same pace. They started at slightly different positions, and they have slightly different personalities. One has already stopped and shouted along the way. The other has been walking in silence, but they are heading to the same place. And that place, in solar terms, is the position of maximum Earth exposure. Forecasters at NOAA update their assessments every day. Every morning, analysts look at the current position of both active regions, measure the latest magnetic complexity readings, compare them to the previous day's measurements, and calculate updated probability estimates for significant eruptions over the coming hours and days. For AR4374, those probabilities reflect its track record. It has erupted before, multiple times. It is an established producer of moderate-level flares. The question for forecasters is not whether it will fire again. At some level, it almost certainly will. But whether the next eruption will be significant enough and aimed directly enough to cause noticeable effects on Earth. For AR4377, the assessment is more careful. The beta-delta configuration means the potential for a more powerful eruption is genuinely present. But potential and probability are different things. A region can carry a dangerous magnetic structure for days without producing anything significant, and then release that energy all at once in a single eruption, or it can dissipate gradually as the magnetic field reorganizes into a more stable arrangement. Forecasters cannot determine in advance which path a given sunspot will take. They can measure the structure, they can track the changes. But the timing and strength of any eruption cannot be predicted with certainty using current science. What they are saying clearly, in the language of their formal bulletins and probability assessments, is that the next few days represent an elevated window of activity. Both regions are in or approaching the zone of maximum Earth exposure. Both carry magnetic structures that forecasters are monitoring for the possibility of increased activity, and neither has yet produced a major eruption during this Earth-facing pass. This is the period forecasters are watching most closely. What happens inside that window, whether it closes quietly or with significant activity, is the question that the entire global solar monitoring network is sitting with right now, and understanding how they monitor that, what signals they watch for, and how quickly they can alert the systems that depend on advance warning is the next part of this story. Let me put all of this in perspective, because when people hear that two sunspots are rotating toward Earth, that one already fired and disrupted radio signals across a wide region of the planet, and the second one may carry an even more powerful magnetic configuration, there is a natural human response: concern, maybe worry, the feeling that something unusual is happening. I want to address that directly, honestly, and with the accuracy this topic deserves. The sun has been producing flares and sending energy toward Earth for billions of years, long before there were people here to notice, long before there were satellites or GPS systems or global radio networks. Solar flares are not rare, they are not extraordinary. In an active part of the sun's cycle, significant flares can occur multiple times in a single week. The sun is a star in the middle of its natural cycle of activity, and what we're watching with AR4374 and AR4377 is the sun behaving exactly as it always has. What has changed is not the sun. What has changed is us. There have been moments in relatively recent history when solar activity produced effects that people noticed, and that made it into the news. Power infrastructure in certain regions experienced unusual stress and required careful management. Satellites had to be shifted into protective modes. GPS accuracy drifted enough to affect precision operations. Radio communications were interrupted for periods ranging from minutes to hours. In some cases, the beautiful side of these events appeared in the sky. The northern lights, some visible from latitudes far south of their usual range, painting the night sky in colours that people who had never expected to see them were completely unprepared for. After the solar wind activity associated with these same active regions passed Earth earlier in the week, aurora reports came in from across a wide stretch of the United States. People in states that almost never see the northern lights stepped outside and looked up, and saw curtains of green and red light moving across the sky above them. Some of them had lived their entire lives without seeing anything like it. That is the other dimension of what solar activity can produce. Not just disruption, but beauty. The same physics that can interfere with a radio signal can also create one of the most striking natural displays the human eye can witness. The key to understanding all of this correctly, the thing that separates informed awareness from unnecessary fear, is understanding the relationship between what is possible and what is probable. A strong flare from A, AR4374 or AR4377 could disrupt radio communications across certain regions again. A powerful coronal mass ejection arriving at Earth could cause a more significant geomagnetic storm. In a scenario with substantial geomagnetic activity, power grid operators, who receive advance warning from the monitoring networks, take protective measures. They have procedures for this. They have done it before. They are not surprised by solar activity. The global infrastructure that runs on signals and satellites and connected technology is not defenseless against solar weather. It is monitored. It is managed. The people responsible for keeping power on and satellites operational have dedicated systems precisely because the sun is active and always has been. What we are not talking about is catastrophe. We are not talking about the end of anything. We are talking about the sun doing what the sun does, sometimes quietly, sometimes loudly, and the modern world responding with the same preparedness that it responds to severe weather here on Earth. The question is never whether the sun will be active. It always is. The question is whether we are paying attention at the right time, in the right way, with the right information. And right now, the right time is this week, as both AR4374 and AR4377 complete their rotation toward the position of maximum exposure. The right information is what solar scientists are gathering every single day, updating every morning and sharing with the systems that depend on it. Which brings us to exactly what those scientists are watching for, and what signals, specifically, would tell them that one or both of these regions is about to produce something significant. Right now, as you watch this, professional solar scientists on multiple continents are doing what they do every single day of the year. They are watching. At NOAA's Space Weather Prediction Center in Boulder, Colorado, forecasters are looking at live solar imagery, updated at very short intervals continuously, and tracking the magnetic complexity of both AR4374 and AR4377. The tools they use measure something called magnetic flux, which is essentially a way of quantifying how much energy is stored and how unstable the magnetic field lines are becoming. Think of it as a stress measurement for the sun's magnetic structure, not unlike the instruments geologists use to measure stress accumulating in fault lines before an earthquake, except that the measurements update far more frequently, and the forecasters can see the sun directly. At the Royal Observatory of Belgium, the institution that identified and published the classification of AR4377's magnetic structure, solar analysts issue regular bulletins that are read by space weather teams around the world. Japan operates its own space weather monitoring centre. Australia's Bureau of Meteorology includes a dedicated space weather division, particularly attentive this week, given that the last radio blackout hit Australian and nearby oceanic regions directly. European space weather monitoring programs track the same active regions and share data across a coordinated international network. This is not a single institution watching in isolation. It is a globally coordinated effort, with data flowing between continents in near real time, giving forecasters the most complete possible picture of what both sunspots are doing hour by hour. Here is what they are specifically looking for. In the period before a major solar flare, sunspot regions sometimes show early signals. The magnetic field lines, which can be measured in detail using specialized instruments that analyze specific wavelengths of light, begin to show increased complexity. Regions within the sunspot that carry opposite magnetic polarities move closer together, increasing the tension in the system. In certain wavelengths, there can be subtle increases in brightness that indicate energy is beginning to accumulate near the surface, rather than deeper within the structure. None of these are guarantees. A sunspot can show these preliminary signals and then stabilize without producing a major eruption. Forecasting solar flares is not like forecasting rainfall, where the physical processes are well understood and the models are highly refined. Solar flares remain genuinely difficult to predict with precision. Forecasters can assess probability ranges, track the evolution of magnetic structures, and identify periods of elevated risk. But they cannot tell you that a flare will occur at a specific time on a specific day. No one can do that reliably with current science. What they can do, and what they are doing, is maintain constant awareness and issue updates as conditions change. If either AR4374 or AR4377 begins showing the kinds of changes that indicate increasing instability, NOAA will update its watches and warnings. Those warnings flow automatically to satellite operators, who can put their spacecraft into protective configurations. They reach power grid operators, who can adjust their systems to reduce vulnerability. Aviation authorities receive them and can reroute flights if necessary. The warning system is not passive, it is an active, responsive network. For a solar flare's initial energy burst, the radiation and extreme ultraviolet light that causes radio blackouts, there is effectively no advance warning. Those effects arrive at Earth at the speed of light, essentially simultaneously with the flare observation. The blackout happens before anyone can be notified, which is why AR4374's earlier flare affected radio communications so quickly and seemingly without warning. But for a coronal mass ejection, the larger cloud of solar material that sometimes follows a major flare, the travel time is longer. That window is where the warning systems have genuine value. Operators have time to act, to protect, to prepare. The next few days represent the peak of the Earth exposure window for both active regions. That is the window the monitoring networks are most focused on. Not because a major event is certain, it is not, but because if either region becomes more active, this is the window when the effects would be most directly felt on Earth. And as of right now, neither AR4374 nor AR4377 has produced anything close to the upper range of what their magnetic structures suggest is possible. The question of what comes next, the three realistic paths this story could take over the coming days, is where we go from here. So where does all of this lead? Let me walk through what the next few days could realistically bring, without guessing, without dramatizing, and without pretending that anyone can tell you for certain how this story ends. There are essentially three ways this plays out, and understanding all three gives you a realistic picture of the range of outcomes that forecasters are holding in mind simultaneously. The first path is the quiet one. Both AR4374 and AR4377 continue producing small, manageable activity as they complete their rotation across the Earth-facing disk. The magnetic energy in both regions dissipates gradually. Whatever was stored in AR4377's compressed magnetic structure slowly reorganizes into something more stable without triggering a major release. The sunspots rotate toward the sun's western edge and eventually out of direct Earth exposure. No significant disruption, no notable geomagnetic activity. The story closes without a major event. This is actually the most common outcome when a sunspot carries a dangerous magnetic structure. Many beta-delta regions in the historical record of solar observation have gone through their Earth-facing paths with elevated attention from forecasters and relatively modest results. The structure was there, the potential was real. And yet the eruption that the structure seemed capable of producing simply did not occur, or occurred only at moderate levels. The sun keeps its own schedule, and it does not always follow the script that its magnetic structure seems to be setting up. The second path involves moderate activity, another flare similar to, or somewhat stronger than, the one that already occurred from AR4374, radio disruptions in certain regions, particularly those in the part of the world that happens to be facing the sun when the flare occurs. A geomagnetic storm reaching Earth within a day or two of the eruption, at a level that is manageable and well within the range that modern infrastructure is prepared for. And for people in parts of the world where auroras are occasionally visible, or even in places where they almost never appear, a possible window to see the northern lights further from the poles than usual. After the most recent solar wind effects from these regions reached Earth, aurora sightings were reported across multiple states in the United States. People who had never seen the northern lights in their lifetimes, in places where the aurora is simply not a normal part of the night sky, stepped outside and witnessed something they will likely remember for a long time. That is a real and genuinely beautiful potential outcome of moderate solar activity during this window, not disruption, wonder. The third path, the one that forecasters acknowledge while being careful about probability, is a more significant eruption. A stronger flare from AR4377, given its magnetic structure. A larger coronal mass ejection with a direct Earth path. More widespread and longer-lasting radio effects across multiple regions simultaneously. A stronger geomagnetic storm that infrastructure operators would monitor and respond to, along with possible aurora sightings across more of the northern hemisphere than usual. This is not described here to frighten you. It is described because understanding the full range of what is possible is the only honest way to discuss a story like this one. Pretending only the quiet outcome exists would be incomplete. Suggesting only the significant outcome is likely would be inaccurate. The truth lives in the space between those extremes, and it is informed by the same data the forecasters are looking at. What you know now, after walking through this entire story, is more than most people know about what is happening on the Sun this week. You know which regions to watch. You understand why a quiet sunspot with a complex magnetic structure still deserves careful monitoring. You know what the monitoring networks are looking for and how the warning systems work. You know the difference between potential and probability, and you know that the people responsible for tracking this are doing their jobs with precision and care. If this video gave you a clearer picture of what is actually happening, share it with someone who would want to know. The people who are curious about our solar system, who pay attention to space weather, who want to understand the forces that quietly shape the world they live in, they deserve accurate information presented calmly and clearly. Hit the like button if this story was worth your time. Subscribe so you're here when we update this story as the situation develops further. And drop a comment below. Tell me where in the world you're watching from. Because this story belongs to all of us. The Sun does not pick favourites. It does what it does, on its own schedule, without asking permission. AR4374 already showed us what it is capable of. AR4377 has so far remained quiet, and forecasters are continuing to monitor it daily, and within the next few days, one way or another, we will know more. The Sun continues to be an active and closely watched subject for space weather scientists around the world, and we will be right here, watching alongside you when the next part of this story unfolds.